All right, one application of exponential functions is looking at investments. Okay, so this is an example of exponential growth. You could change this here. A grade 12 student chooses to invest. You could say a wise grade 12 student chooses to invest in a term account which pays 5% per year, even though that's a lot higher than you're going to get these days, compounded annually. If you, the reason I say wise grade 12 student is if you wait till you're 55 or 50 to start investing for retirement, look at the shape of that graph. Because investments compound interest grows exponentially. If you only have 5 years to wait for it to grow, it's not going to grow very much, right? Whereas if you have a long time to let it grow, what happens to this curve eventually? Like this curve keeps going like this. The power of compound interest is leaving it there long enough that this can happen. Okay, so whenever you're talking about investments, the key is having enough time to let it ramp up like that. If for some reason you had some phenomenal interest rate, it's going to happen quicker, but typically you're going to have those low numbers. 5% is even lower than this. This was actually 10%. 1.1 is actually like 110%. So it's growing at 10%. We'll get into your investment strategies later on, maybe. Not that you should take my advice for anything, but I can at least show you the math behind it. So we have our wise grade 12 student investing $1,500 in some term account which pays 5% compounded annually. We're going to write a model. Okay, this is mathematical modeling of a real situation. Our model function is going to be exponential. What's happening with this? Every year you're getting 5%. So you're starting with, I'll write it up here. You're starting with 1,500. After 1 year, what are you multiplying it by? You're multiplying it by, what are you multiplying by? Yeah, you're multiplying by 0.05, but that's going to give us just the interest. If I multiply by 0.05, that'll give us how much interest we have. $75 or something like that. But I want to get the final answer. I want to get the total. At the end of 1 year, I have the 5% interest, but I also have the original amount, right? At the end of 1 year, I don't just have 5%, I have 105%. Let me pause here to show you. Okay, so this represents, this 105% we're going to multiply by here, represents the original amount of money, the principal plus the interest. If we want to get this in, maybe in grade 8 you learn to, somebody says, what is 5% tax or 5% interest? So you would go 1,500 times 5%. You'd get an answer for that, and then you'd do 1,500 plus 75, and you'd say it's 1,575 or whatever. That's kind of the slow way. The quick way would be to just say 1,500. At the end, I've got 5% and the original amount. You can just multiply it by 105% and get this right away, get that amount. Because then all you have to do is every year you're multiplying by 105%. After 1 year, you've multiplied by 105% once. After another year, you've multiplied by 105% again. You just keep multiplying, right? Whatever you had at the beginning, you multiply by 105%, and that gives you the new part. So our model function is going to be our starting value. Just the same way before we had y equals 100 times, what do we have? 1.1 to the x. Except here our starting amount isn't 100. What is it? 1,500. And our rate isn't 1.1. What's our rate? What are we multiplying by every year? 1.05. 1.05 is actually lower than 1.1, so it's not going to grow even as fast as 1.1. 1.1 would be like 110%. This is the model function we're going to use to look at this, okay, to represent this. Get rid of that. That was just our example. Okay, that's our model function to model this situation. If you wanted to know how much you have, the accumulated amount after 3 years, if you want to know it algebraically, how can you find that? Yeah, just put x is 3, so just go y equals 1,500, 1.05 to the third. Again, you could look at it on a spreadsheet, right, the way we did, or you could look at it on a table on the calculator. There's a lot of different ways to do it here. If you put it in this, on a spreadsheet, it's just quicker than the calculator, but and a lot more powerful, I would say. We're starting with 1500. That's growing as though it was 10%, right? Because remember I multiplied by 1.1, but I don't want that. I want to grow at 5% here. This is now 1500. Now there's two ways I can do this. I can say 1500. I can say the previous cell times 1.05, right? That's one way I can do it, because then it just says take the previous value and multiply it by 1.05. The other way I can do it is I can say, the way we just did it with the function, I can say every single one of them is 1500 times 1.05 to the power of what's in this cell, right? What x is. That's x. Oops, what happened there? Why won't it let me put that in there? D1. Oh, because I didn't put equals, that's why, of course. 1500 times 1.05 to the power of, this is x, right? So there's x. So instead, then I can just follow that down now, right? The next one's going to be 1500 times that. On a spreadsheet, you can just, it's going to give you the same values. It's just defined a different way. This way is defined by saying the previous one times 1.05. This one's the way that we don't have to do all of these. Like if you were doing this by hand, you'd have to do every single one. If you wanted 10, you'd have to go down and figure out every one before of it to get there. Here, writing it as a function, saying it's 1500 times 1.05 to the power of that, x, right? To get this one, you can put that in there, right? If we want 29 now, or if we want 56, you can get that, right? You can get that value. Whereas this, we'd have to keep scrolling down the list. On your calculator, you can do the same thing. Generate a table like that if you want. Or, of course, you can just sub in the value, as you suggested before. 1500 times 1.05, power of 3 if you want 3. Okay, that value. You can set up a table by putting the equation in. 1500 times 1.05 to the power of x. You could look at the graph. If we looked at the same window, it's probably not going to go up as quick as the other one because the numbers, it's going to start higher because we're starting at 1500, so I probably have to make sure I go up that high. Maybe we'll go negative 1,000 to 5,000, 500s. Now I've changed the scale so it's hard to compare to the other one. Okay, the one that we had before. The other one we had before was $100 or 100. We started with 100, and we had it growing at 110%, right? You don't have to put the 0, but if you want to compare, that would be growing at 10%, starting at a much lower value but a higher interest rate. Doesn't look very good, eh? Which one's a better investment so far? It's pretty obvious, right? What do you think is going to happen if we keep going to the right? Any ideas? You're not sure, eh? Let's go 50 years. So you're the wise grade 12 student invested, and you're looking at what's going to happen 50 years from now when you retire. How high do we have to go here? Who knows? $20,000 maybe? Okay, there's our $1,500 and growing at 5%. Here's our, can't even see it yet. Here's our $100 growing at 10%. What's happening there? Is that gives you more insight as to what's happening, I think. What's going to happen? You have to wait a long time for it to catch up, but eventually it's going to catch up. If one's growing at 10% and one's growing at 5%, it's going to catch up. If you go to 70 here, I know this is riveting stuff, but especially when you have to watch the slow calculator. Oh, maybe it's going to be off the screen now after all that. Come on, you can do it. Oh, almost. Anyways, you get the idea, right? If the base affects how curved it is, if the base is bigger, it's going to eventually catch up. Even if you start with a lower number there, right? It's going to eventually catch up. I am almost at 10. Can you think about how you're going to determine this graphically? I'd like you to know how to confirm things find them algebraically, find them graphically. I have that graph there. We'll do that in a second.